Okay. So when one studies phase transitions, one typically works with what we are using here in a very natural way. When one works with an ordered parameter. So a variable that quantifies the symmetry breaking that happens when we cross through the critical point or the Curie point. Critical is a complicated word, but through the transition point, we cross from a high symmetry phase to a low symmetry phase. In the high symmetry phase, in our case, P is equal to 0. In the low symmetry phase, is different from 0. Now, typically, if you look at ferroelectrics, ferromagnets, you have, in any sort of transition, a very interesting quantity, which is the susceptibility associated to the order parameter that becomes different from 0. Okay, this could be the magnetic permittivity. Here is going to be the dielectric susceptibility. So this susceptibility tells us how easy it is to change the value of the order parameter when we apply the conjugate field, which here is the electric field, of course. Okay, there is always a susceptibility, by the way, but ferromagnets in ferroelectrics are special because the conjugate field is very simple. It's just an homogeneous electric field or an homogeneous magnetic field. In other cases of ferroelectric or of structural transitions, the conjugate field may not have a simple physical realization in an antiferromagnet. Okay, so we are going to pay a little bit of attention to this quantity, the susceptibility, which we define as the derivative of the polarization with respect to the electric field, for whichever state that we want to look at, but here we are going to look at the state of 0 electric field. Okay, so now part of the interest of this exercise, well, this exercise is interesting for many reasons, but part of the interest is to see how we can compute non-trivial behaviors from our equation of state. So here we are going to have to take a derivative, and generally this is actually a partial derivative. For example, we are going to assume implicitly that when we put an electric field here, the temperature is not going to change. This is actually an assumption that is implicit. Well, here we are going to make it explicit because I'm already talking about it. It's implicit in the books out there. It won't even be mentioned, but in fact it's a non-trivial assumption, because in a ferroelectric, application of an electric field changes the temperature in general. Okay, that's called the electrocaloric effect, and people use this for refrigeration, for example. So we are going to try to make those assumptions explicit. Okay, what I want you to pay attention to is that this expression, this little formula we have here, we have called the equation of state. This has to be true for any equilibrium state. Okay, but it also means when you have an equation like that, it means that if you make a variation of any of the quantities here, it could be the temperature, the polarization, or the electric field. This equation of state tells us that if the polarization changes a little bit, for the equation to be satisfied, everything else also has to change. Or if the electric field changes a little bit, if the equation needs to be satisfied, everything else has to change. And we can analyze these changes in the limit of when they are small by taking the differential form of that equation. So here we are going to assume that the only two things that can change are the polarization and the electric field, and that they can change independently. Okay. So if I take this equation and take the differential form, that's going to look a little bit like this. dp dp So all you do when you take a differential form like that, as you can see, is to take the derivatives of the terms with respect to the variables that can change. In this case, this term with respect to the polarization, this term with respect to the polarization, and this term with respect to the electric field itself. So you take the derivatives and you multiply by the amount of change. So the amounts of change are not independent. If the system remains in equilibrium and I change the electric field, the polarization has to change exactly by the amount given by this equation. That's what guarantees that our equation of state continues to be satisfied. But now, of course, if we have this, and by the way, as I have already said, here we are assuming that the temperature doesn't change. If the temperature changes, here we will have an extra term that will be like alpha prime p dt. Okay, which is the derivative of this thing with respect to the temperature multiplied by dt, the change of the temperature. So let's forget about this one for it. Okay, so the equation of state tells us how our variables have to change together. And when we have something like this, for this very particular quantity, we can kind of deduce it immediately, right? So if we divide everywhere by dE, I have something like this, T minus Tc over here, plus 3 times beta P squared. And as a common factor, I can take dP dE, which I can identify with this partial derivative if I recall that the temperature, for example, is what is being kept constant, right? Okay. And maybe the strain is also, or the stress is also being kept constant, that we are not even worrying about right now, but eventually all that can be made explicit, right? So I can essentially write this, and this is at constant temperature, at constant everything that we don't worry about. That's implicit when we write something like that. Okay. So this means that dP dE equals the inverse of this thing. Okay. Now this expression is general. Here we are not saying anything about the temperature at which we are. This has to be true for any temperature. Actually, this expression is also independent of the electric field, because never have we imposed that the electric field is equal to 0. So a totally general expression for the susceptibility we have obtained. So let me copy it here, and we are going to evaluate it. So dPdE, which is equal to epsilon 0 chi, is alpha prime T minus Tc minus 3 beta P squared. Now, I also here, we can point out something that it may not be very obvious from here, but it will actually always be true, which is that when we have taken this differential form, we could have taken, we are essentially taking the derivative of the whole thing with respect to P and multiplying by dP, right? So we could have grouped these terms, and that makes it very obvious that this object here is, in essence, the second derivative of the free energy with respect to the polarization 2 times, and this object here is exactly the stiffness that we had computed before. Okay, so the susceptibility is the inverse of the stiffness. It is the inverse of the stiffness. As simple as that. So now let's evaluate the susceptibility. And this is something that we have already done, because in the previous lesson, we work out the equilibrium polarization in different temperature ranges, right? Above Tc and below Tc, that's it. And we work out the stiffness. So the inverse of that quantity is actually the susceptibility. So now let's pay attention for a moment at how that looks like. So we had two solutions at zero field. Here is where we are imposing zero electric field. Okay. Now we are going to look at the solutions of the equation of a state at zero field, which are the ones that we have already discussed. Okay. And when we evaluate the susceptibility, therefore it will be the susceptibility at zero field. That's where we are imposing zero field. So we know that we have P equal to 0 for T above Tc, and this gives us a stiffness that is simply alpha prime T minus Tc. And we had a second solution, which was something like P squared minus alpha prime t minus tc divided by beta. These solutions exist and are minima for t lower than tc, and they give us a stiffness, if you recall. I mean, by plugging this in here, we get that kappa is minus 2 times alpha prime t minus tc. So we have a very, very interesting situation. Now, we didn't do it before, but we can plot these stiffnesses as a function of temperature, recalling that the susceptibility is simply the inverse. If we plot them, this is a very nice plot. Temperature, our special temperature, Tc. What do we have? Above Tc, we simply have a linear dependence. So positive slope is clear, and the stiffness goes to 0 exactly at Tc, right? I mean, so we have something like this. Okay. And below Tc, we now have a negative slope. Kappa is always positive, by the way. You see that. And the slope is twice as big in magnitude as it was before. So if before we had a certain angle here, now we have it to have it twice. So let me approximately plot it like this, okay? But this slope is twice this slope, and with a different sign. Now, what is amazing is that many ferroelectrics, this can be straightforwardly measured. You measure susceptibility as a function of temperature in a ferroelectric with a continuous phase transition or approximately continuous phase transition. You can plot the inverse of the susceptibility, and you will see approximately linear behavior with the relationship of slopes of approximately a factor of 2. This happens in many, many materials. In some of them, it's really incredibly accurate. In others, it's an approximation, but this is still generally true. Okay. Now, if we plot the susceptibility itself, it's a bit more difficult, but it's worth plotting it to emphasize a point. The susceptibility is simply the inverse of this. Kappa is always positive, the susceptibility will always be positive. It better be. When you apply an electric field, typically the polarization grows following the field. If it doesn't do that, then you have to think harder about what's going on. Okay? The electric susceptibility is positive. Of course, here the stiffness goes to 0, so the susceptibility in this very simple transition essentially has to diverge. So it diverges from both sides, and it will diverge at a slightly different rates, let's say, because it will diverge faster over here. Over here? No, over here. Okay? So it will be something like this and something like that. I'm trying to plot it so that this guy. No, the other way around. It diverges. No, this way, this way. It diverges like this. Okay, the details are not important, but we have an infinite susceptibility. And I want to make a point here, of course. This already starts giving you the feeling of why ferroelectrics are very interesting. Ferroelectrics are materials that have some key quantity of any material, like the dielectric response, so response to an electric field, has an anomaly that makes the electric susceptibility very, very large. Of course, you never measure infinity, but it's not uncommon in ferroelectrics to measure susceptibilities of 10,000, 40,000. Where, just to give context, silicon has susceptibility of about 10. Okay? So if you want to make a material that is reactive to electric fields, or that can be, whose behavior can be changed by applying an electric field, a ferroelectric is probably your kind of guy. Okay, that's one thing. But another thing that is very interesting here, and that sometimes leads to confusion, so I want to make the point, is what does it mean to have a divergent susceptibility? Having a divergent susceptibility seems to imply that if we apply an electric field to this material close to this region, we will get an infinite polarization. And that is not true. That is not true. If we think about the energy landscape, you see that a divergent susceptibility boils down to having a zero stiffness, which means a very flat, totally flat, in fact, energy landscape around P equal to 0. That indeed means that to change the polarization at that temperature costs no energy. You apply an electric field and the polarization will overreact. But eventually, the polarization will be controlled by the other part of the energy, this beta term. Okay? And this is really how the physics works. So even though before, when we were working out our simplest lambda potential, we said that high energy is a parabola is enough. Well, above TC, a parabola is enough. But close to TC, we certainly still need the fourth order term. Because it's not true that by applying an electric field we get infinite polarization. So there must be something that prevents the polarization from being infinite. And that is the fourth order term in the lambda potential. Okay? So you see, the polarization never diverges, really, because you have immediately, if you want, higher order parts of the response that control the value that it can take. But more to the point, when we have a divergent susceptibility, we should not understand it as an infinite response to a finite perturbation. Rather, the right way to understand this is that if I perturb the system infinitesimally, so if I use a very, very small electric field, I get a finite response. That is a much more physically appropriate way to understand a divergent susceptibility. Okay? It's a system that reacts even if the perturbation is infinitesimally small, rather than a system that gives you something infinite for a finite perturbation. All right, so this concludes this part. I'm going to stop that.